meeting, so I'll try to make it tight, and these are the things we should discuss today. First, I have shared with most of the people who have signed for the course few books in Gmail, so I want to tell a few words about them. After that, we should make a definition of a few parameters like charge, voltage, current, resistance, conductivity, the time, frequency, what we mean when we say some linear and non-linear devices. After that, we have time for the properties and characteristics of semiconductors. So this is the basics. It's very theoretical, but this is needed in order to understand the difference between devices. So if we can someone close the door, please? Because if you open some catalog with devices, they are all under transistors, they are all divided by some other type, bipolar or some kind of FETs and so on, but the difference is in the physics of these devices, and the models that are going to be used in the simulators later are actually these parameters, which is the basics of which are the basics. So this is a little bit theoretical, but without this we are doing nothing, so I believe it's going to be worthy. Probably, I'm not sure if we are going to discuss the diode circuit today, but let's see. So about the books. The first book I recommend is Microelectronic Circuit Analysis and Design. It's written by Donald Niemann. He's very famous professor from Brasilia. He's Brazilian, I believe so. But he has a lot of experience in teaching, and actually because I'm not very good in English, that's why I have copied and pasted some of his some things of his book, and I'll make explanations on them, and I'll use some of his words because sorry, doesn't matter. Semiconductor physics and devices is a little bit, this is the same author, but it's more complicated book. It's about devices, their physical properties, and more theoretical. So you can leave this book for now. Data of electronics is something like classics. You can use it as a reference, and I haven't said that these books are quite big. They're about 1,000 pages, and nobody can't read them all. When you need something, they are divided by some there's agenda and the chapters, and so you can look what you are looking for. Very descriptive book with lots of circuits in it, examples, and calculations in the book, so you can use it as a reference. CMOS circuit design layout simulation is written by Jacob Baker. He is a teacher at some university, and this is his website, CMOS Edu. He is doing he is making RAMs and analog devices, and he is teaching few courses in this in this university. I can show you actually the page. It's very useful. He uses electric as a software, and LT-Spice to simulate the circuits. We can read here about Jacob Baker, and the courses that he teach are here. He has also video records of his courses, not all of them, but most of them. So, for example, here on lecture notes, you can see a video of his lectures. So, for example, introduction, start chapter 9. This is from this book, which I have told you previously, Circuit Design Layout Simulation, 3rd edition. He's explaining very good the things with examples and so on. If someone wants to learn a lot more, for example, here is some operational amplifier that they are discussing, and actually it's a very good source for references. So his book is also very good, with lots of examples and so on. I wanted to show you just, for example, this guy is working on few things, and the last one that I read was this circuit. It's called memristor. It's one of the elements that are very new. The technology is very new, and he's making the control of this memristor. So the device is there, and they need to make it work. And the memristor is resistor which can be programmed to be with different resistance through current. When you drive this resistor with some amount of current, it changes his resistance and memorize it. After that you can use it. It will be very useful for analog designers, because you can program the resistance as you like. So it's very interesting, and actually you can read the article if you want. It's free. Just so this is the key point, and he is explaining some kind of things about it. So this was my introduction about the books. Because probably you are going to use them as references later when you try to make some circuit by yourself. We are going to discuss the particles and some electromagnetic observations. So in general, when we look at the physics, I understood that there are four basic forces, and they can interact between each other. So these forces are defined as strong, electromagnetic, weak, and gravitation. So these four forces can't be explained by anything else. So they are used as a reference. This is simple copy of Wikipedia about the charge. In particle physics, fundamental interactions, sometimes called forces or fundamental forces, are the ways that elementary particles interact with one another. So the charge is one of these fundamental property or forms of matter that exhibit electrostatic attraction or repulsion in the presence of other matter. So I won't read everything, but the thing is that we have charge all around us. It's in the air. Also, we have particles. These particles are charged, either positive or negative. And the thing about charges is that you can measure some. If you take some place in this room and take other place in the same room, for example, or somewhere else, there will be a different amount of charges over there. So we can measure the difference between these charges. What does it mean? It means that if we apply some voltage over there and we have a wire connection or some metal, a current will flow between them because of these charges. So I'm not sure if you understand everything, but the voltage is defined between two amounts of charges. So the voltage between two ends of a path is total energy required to move small electric charge along the path. So if we want to make this charge move from one place to another, we have to apply a certain amount of voltage. This is meant here. And it's very simple, actually. We are measuring voltage between 2 points. It's not. We can't measure voltage on a single point. I mean, there's no physical explanation, and when you measure the voltage, you have to always to define the reference, because if okay, let's leave it like this. Does anybody understood what I was speaking about? Or someone, does anybody have questions? I mean, it wasn't very obvious what I meant, but
So what is the difference between two charges?
what is the difference between two charges?
Voltage is the difference between two charges.
Yes,
No.
Potentials.
Yeah.
potentials, yes, but the charges are the components that define the potential of the system. So we have a potential difference between these charges. Do you?
Potential difference between two places.
Yes.
And the potential difference is generated by the electromagnetic field that flows between those two places, and the electromagnetic field is generated by the charges.
Yes. Okay. By convention, yes. Okay. This is good explanation.
I still didn't completely get it, I'm sorry. You write here to move a small electric... No, the other page is more important for me because it's shorter. To move the small electric charge along that path divided by the magnitude of the charge. The magnitude of the charge, I understand, is the same as a small charge. The magnitude is the size of it, right?
Yes.
So
This is the small.
to move a small electric charge divided by the magnitude of this. So I don't understand that. Is magnitude equals small?
If you need to move a charge in electric field, you need to apply energy. Take it here and put it there. So the difference is the amount of energy you need to apply divided by the magnitude of the charge. That means the bigger charge, the more energy you need.
Yes.
If you're asking why is it small charge,
Yes.
is it small because if you put a big charge and you can distort everything else around it. So it's not the same field anymore.
Okay. Alright, thanks.
Има концепция за елементарен заряд на материя математически. Стане много задълбано.
Да, то проблема е, че
Този заряд
това е много...
в случая е елементарен заряд, който има единица.
Да, т.е. определен там 10 на минус 19 и така нататък. Става въпрос, не съм искал да влизам в някакви големи подробности. So the current, electric current flow is a flow of electric charge through a conductive medium. So this is understandable. And in electric circuit, this charge is often carried by moving electrons in a wire or some medium. It can also be carried by ions in electrolyte or by both ions and electrons as in a plasma. And the C unit for measurement the rate of flow of electric charge is ampere, which is charge flowing through some surface. So you have сечение, знаеш как е? Cross section of some medium, and the electrons that flow from one side of this cross section to the other is actually the electric current. Simple explanation. Time is the order of events from the past through the present to the future and measure of the duration of them and the intervals between them. We are defining time, and after that we can measure the frequency. It's obviously that
find the time in terms of the season 110 so atom two super thin electron
I didn't catch that. If we can measure a small amount of time, you mean?
The definition of time, the modern definition of time,
Can you say it?
is based on the cesium atom.
That's the definition of a second.
So the second,
Yeah, not time. Time is not definable. It just is.
It exists actually, but
it is measured in seconds.
yes, the frequency is the number of occurrences of repeating events per unit time. It is also referred to as temporal frequency. This is also Wikipedia, but actually if we have some periodic signal which is defined in time, we can find its frequency. It's 1 over t over the period of the wave. Yes, actually I can show you a simulation so we can see what is this in we know what is voltage now. We have this is a voltage source, but okay, I'm setting actually the reference point between one of the points. It's called ground. We will see later. And okay, so have to place a simulation, transient analysis, so we can see the time, and it's measured in milliseconds. Here I can define the frequency or the period of the, it's actually the period of the signal. We will see it in the simulation, but for now I'm going to use 1 megahertz as a reference. Why? Because we are going to define here 10 milliseconds, and let's see what's going to be the output. I'm making these simulations to show you how you can use simple how to use simple simulations to, when you don't know something, you can actually simulate it to see how the things are working. I believe it's a good way to learn the simulators. So we have 0. Why? We have to place labels, I think so. bug in the program, I think. No, it's okay. It's not working as I think, but let's see. Strange. The minus is here. 8 seconds. We have too small amount of points, so I'll place here 400 for example, and we'll simulate just 1 millisecond of this voltage source. So if you see here, we have a periodic signal with amplitude that is some kind of oscillating. Why is this? I'm not sure. We have to lower the we have to make it 0.1 millisecond, so if you want to see the whole wave. Actually, the period is from here to here, and now you have to change a little bit my mathematical, so a little bit better. We can even improve it. Okay, now looks much better. So this is the period, and the frequency will be 1 over this period. So it's 1 megahertz. It's actually we have defined it over here because it's 1 to the minus 6, isn't it like this? Does everybody see this? I mean, frequency and time. We have to be very flexible, and we have to be able to switch between time and frequency, because the integrated circuit work at high frequencies. They have sometimes combinations of a lot of frequencies, and actually with different type of frequencies we can manage to define some rectangular or some other type of signal in time domain. So there are two domains. One is frequency, and the second one is time domain. We will discuss this when we get to simulators, but the thing is that you can define the signal in frequency domain and see what will be how it will look in time domain. For example, do we have some? Yeah. For example, if we have a rectangular pulse or something like this, it consists, this is in time domain, and here is some kind of voltage. The period of this signal is t, but if you look at frequency domain of this this periodic signal, it's also periodic, but it's not sinusoidal. So it will consist of a lot of frequencies that will define the shape of this rectangular signal, and they will be in small, how to say,
maybe you have to think about something about Fourier maps and polynomial.
we will go there.
This is exactly this. You can represent.
Yes, I just want to have to show the people the idea about the frequency and the time, and that sometimes it doesn't mean when you see something in time domain it looks the same in frequency. Actually, it's much more different. But the filters, for example, are such things that define the signal in frequency domain. You can shape it more or less the signal, and when you look at it in time domain, the signal will be defined as you wish. Actually, sometimes the frequency is much more relevant for our analysis, and sometimes the time domain is much better to analyze some circuits. We will look.
Does time domain always mean according to voltage, or is this?
Actually, usually we are measuring voltages, so it's also possible to measure the with oscilloscope. You can't measure the current. Usually the current is measured with a voltage drop on a reference resistor. So when you know the resistance and when you know the voltage and the shape of the voltage, you can measure the current flowing through this resistor. We will define the resistance and conductance. The resistance of electrical element is opposition to the passage of an electric current through that element. So we can make different resistances with different type of materials. For example, nickel chrome. Some metals are usually used, and the shape also can affect the resistance and different parameters. So electrical resistance is defined actually this voltage that we defined previous divided by the current. It's actually the ratio of voltage across it to current through it. If we have some circuit with 2 pins, there is a voltage between these two pins, and if a current flows through it, we have defined we have a resistance. We can define this resistance. So what can we say about this in the simulators? We have here a voltage generator. We have ideal resistors, and if we want to actually if we want to define some current or resistance, I didn't want it to go in this direction now, but okay, we can place a resistor here, and what I want to show you is that we can control the current through this resistor by changing its it's obvious actually, but let's see how it's done in simulator. If you want, you can actually use it as a voltage divider. If we place two resistors and take one of its output here, it will divide the voltage. For example, if we have two resistors with the same value, 50 ohms, let's see what is going to be the output here when the voltage is alternating. So this we have a DC and AC parameters of devices. The DC parameters are usually shown with caps lock, or how would say upper cases, and the alternating parameters like voltages and currents are defined with small caps, so you can easily distinguish between them. So output is you see that between the input and the output in time domain there is a voltage difference. If we place here a measurement a marker, we can measure here the voltage. It's obvious that it's half the voltage of the input, so we just did a voltage divider, it's so called. how can we see what is the current here flowing through this? The current is the same because we don't have branches, or we have defined the current through in this circuit. It's obvious that the current will be the same for both resistors because we don't have any other branches. Actually, you can look at these blue lines as a wires. They are physically connected, and if you solder this circuit, you should place wires over there. So it represents a physical connection. You can't make a circuit without actually the current can't flow like the voltage. It can't be between 2 points in the on the schematic. Yes, it should be connected to ground or some other part of the circuit. When we get to the transistors, you will see this. But the current we can see from the DC bias parameters, and yes, okay, we can place some kind of probes. We have current probe here, and because it's common current, we can measure it. So if we place here the current, okay, you see that the current is also positive and negative because of the voltage, and I believe we can put it on the right axis like this. So the current flows from, where is it?
It's behind the purple line.
Yes, they are one over another, because the current follows the voltage source. So this is a passive circuit. It doesn't have anything to affect its parameters. So it's quite big actually, the current here, because
10 milliamps.
why milli?
1 volt na 100.
Yes.
1 volt.
Okay. It's not so big.
So
Yes.
1 milliamp.
Exactly. Yes. Okay. Conductance is defined as electrical resistance 1 over the resistance. Actually, this is the formula, and it's measured in Siemens. So you see that here the resistance is defined by voltage divided by the current flowing through this device, and here is the conductance is the opposite. The current is divided by the voltage. It shows actually how both of these parameters show what is the not the medium, but the capabilities, yes. And okay, the capacitance. The capacitance is the ability of a body to store an electrical charge. This is the same charge we spoke about at the beginning. It's defined here, divided by the voltage. And the capacitance is measured in farads. Usually the capacitor is parallel plate capacitor. It's two metal layers and some kind of dielectric between them, and the dielectric defines the capacitance of the circuit. So if you have for example very close lines, one to each other or one between one on top and one on the bottom, as I've shown you in the integrated circuit last time, there will be some kind of capacitance. So this is the idea behind that. The parallel plate capacitor is directly proportional to the surface area of the conductor plates and inversely proportional to the separation distance between the plates. So if we increase the distance between the plates, the capacitance will be smaller. So it's not obvious here from this formula, but okay.
Where is the difference between a capacitor and a battery actually? Just the next point.
Yes, actually you can look at the battery as some big capacitor, but the battery is using some kind of liquids and
like a chemical reaction.
Yes, it uses chemical reaction to get this to get the voltage, actually the voltage difference between the plates, and it also has capacitance. The battery has self-capacitance. You can't charge the battery. Okay. So there are different they are physically different, but the capacitance is a parameter one of these basic parameters like charge, like resistance and conductivity in the electromagnetism. There is a field theory, and this is one of its basic parameters. So we can go deeper in this area, but I don't think it's very necessary to. We can use these parameters as defined, and we should be able to know how they are affected if we place something around them, or how they will interact with our circuit. So after a while we are going to make a break. So just the inductance in electromagnetism is that property of conductor by which a change in current in the conductor creates a voltage. It's actually electromotive force in both the conductor itself. This is called self-inductance, and nearby conductors. It's the mutual inductance. Yeah, this effect is used in transformers, and with this mutual inductance is defined the transformation ratio between the windings, and actually you have two wires somehow connected, not physical, but they are very close one to each other, and by the windings and the distance between them we can define the transformation ratio, and actually this is the mutual inductance. This effect derives from two fundamental observations of physics. First, that the steady current creates a steady magnetic field, and the second, that a time varying magnetic field inductances voltage in a nearby conductor. In an electric circuit, the changing electric current through a circuit that has inductances induces a proportional voltage which opposes the change in current. So the simple thing is that the alternating current through some wire or something, some media, if we have some big inductance, the current will try to stay in the same direction when we remove the voltage. So if we want to just a second to so the current to flow, we need first wire, and the second one is a voltage drop. It's a physical thing, we can't go without it. If we make some windings on the wire, we will increase the inductance, which is this parameter, and after applying alternating current, this current will try to resist when we remove the voltage, this current will try to stay in the coil, yes. And actually this is it will produce some kind of small voltage drop. So we remove the voltage, but the voltage stays there just because of this inductance. I'm not sure if you have understand it, but we will see these effects in the circuits later, so we will have a chance to make it understandable.
It's like a capacitor in this situation.
It's like a capacitor, but in the opposite direction. So the capacitor, for some frequencies, we can define the resistance of the capacitor and resistance of the inductor for some frequencies. For these frequencies, if the circuit have a capacitor characteristic, this characteristic will be with negative sign in front of this resistance. And if we have an inductive character of the circuit, it will be with positive sign. This is how the RF circuit works. Yes. Actually, the
capacitor has zero resistance on high frequencies and high resistance on low frequencies. An inductance has no resistance on low frequencies and very high resistance on high frequencies. It's done the other way.
Right.
yes, that's very easy explanation. Linear and non-linear devices, probably everybody knows linear relationship between the current and output voltage. The resistor is typical case. Also the transformers, capacitors, inductors, they have linear characteristic between the voltage and the current. So non-linear devices are elements like diodes and transistors. So sometimes this is interesting. Fundamental non-linear devices like transistor are often used to build approximately linear circuits. For example, operational amplifiers, which we will build at the end. And I think we have to make some kind of pause for 10 or 15 minutes, and we'll continue after that.